This video is an introduction to Karnaugh maps. It assumes that you're already familiar with logic gates like AND, OR and NOT, and how these gates can be combined to produce more complex circuits. You should know about truth tables and how these can be used to describe the behavior of logic circuits in terms of inputs and outputs. It's also assumed that you're familiar with some Boolean algebra, specifically how various rules can be used to simplify Boolean expressions, and therefore the role of Boolean algebra in circuit design. So what is a Karnaugh map, or a K map as they're sometimes known? It's a special form of truth table which enables easier pattern recognition than a truth table does. It's a pictorial method of simplifying Boolean expressions. Good for circuit designs with up to 4 variables, that's 4 inputs. So let's look at an example. Here's a simple truth table with 2 inputs, or shall we say 2 variables. You should recognize this as the truth table of an OR gate. Column F contains the output value for each combination of input values A and B. Strictly speaking, this is the truth table for any combination of logic gates that behave in the same way as an OR gate. So we could say that this is the truth table of an OR function. That's why we've called the output column F. To construct the corresponding K map, we draw a grid with 1 square for each row in the truth table. The possible input values for A are used as column headings across the top, and those for B as row labels down the left-hand side. These input values will act like coordinates for the output values. Now we can populate the K map. We can see from the truth table that when A is 0 and B is 0, the output is 0. When A is 0 and B is 1, the output is 1. When A is 1 and B is 0, the output is 1. And when A is 1 and B is 1, the output is 1. Our K map is ready for use. We'll see this particular one again later. Now let's talk about how a K map can be used to derive the simplest possible Boolean expression. Here's another, different truth table, again with 2 variables A and B, but the outputs in column F are different this time. The corresponding K map looks like this. To derive the simplest Boolean expression from the K map, we're looking for the largest possible grouping of 1s. An expression can then be derived by inspecting this group. Here we can see that whenever there is a 1 in the group, the value of input A is 1. We can also see that the topmost one in the group corresponds to a value of 0 for input B, but the other one in the group corresponds to a value of 1 for input B. This means that the output is independent of the input value B, which makes B a redundant input. This grouping can therefore be expressed simply as A. The output of this function is A. Here's another example with 2 inputs. We've seen this one before. It's the truth table for an OR gate. But let's see how we can derive the Boolean expression by inspecting the K map. Here's the corresponding K map. A single group cannot be L-shaped. So what we have here are 2 overlapping groups of 1s. The 1s in the vertical group always match the input value A. The vertical grouping can therefore be expressed simply as A. The 1s in the horizontal group always match the input value B. So the horizontal grouping can be expressed as B. Hence, this K map represents the expression A or B. It is indeed the OR function. In this truth table, the output is always 1, regardless of the inputs. Here's the K map, which matches this truth table. We can create one large group of 1s here. Clearly, the output is independent of all of the inputs. It is always 1. So the Boolean expression for this circuit is simply 1. Let's consider one more example with two variables. Here's the K-map which matches this truth table. We have two groups here. The ones in the vertical group are always the opposite of input A, so they are related to it. This group represents not A. The ones in the horizontal group are always the opposite of input B, so this group represents not B. Hence, this particular K-map represents the function not A or not B. You may have already recognized that this is the truth table of a NAND gate.